Welcome to another part of the Advanced Natural Language Processing course. Today, we're going to talk about one other very interesting application, which is text summarization. Our outline is going to be as follows. We're going to start by the definition and the summarization problem statement. There we're going to build up the intuition towards summarization. We're going to understand what is the problem, what are the different aspects within text summarization, why do people need the text summarization, and so on and so forth. Then we're going to fly over the evaluation metrics and multiple data sets that we have within the field. Then we're going to explore a couple of algorithms which are suited for conventional extractive summarization. Then we're going to go beyond conventional extractive summarization and see an algorithm which figures out the problem, which solves the problem in a slightly different way. So let's start the journey right away with a text summarization definition. So what is text summarization? It's the task of producing a shorter version of one or several documents that preserves most of the input meaning. Sometimes you also get this problem referred as single document summarization or multi-document summarization. And then a key challenge with respect to summarization is really to optimally compress the original document in a lossy manner so that the key concept within the document is actually preserved. So actually reflecting also on the machine translation part, within the machine translation, the translation is expected to be lossless. Is yet one similar, or like in terms of also approaches, it has a lot of similarity in a sequence to sequence problem, the machine translation, which has been covered previously within this course. Now talking about summarization, we are talking about a lossy manner, not a lossless manner anymore. If you see an example here, there's a bigger document talking about natural language processing with multiple steps, multiple points, and then there is a concise, a shorter version, which actually defines what is natural language processing in a more concise way. Let's go even more. Based on Buffer magazine, 55% of visitors read the social media articles for 15 seconds or less. This means that for them, if they actually manage to get a gist for 15 seconds to cover the idea and the intuition and the perspective that is within the social media article, they grab the attention of the user. They made them take the gist out of the article. The ratio between the length of the summary and the length of the source document is calculated by a compression rate. And a compression rate is defined by the length of the summary over the length of the source document. And a study in 1999 shows that the best performance of the automatic summarization systems are found with a compression rate of tau equal 15 to 30% of the length of the source document. Maybe you're also thinking about it right now from the new approaches or from the new world, but still, I think, or from my own perspective, this is still linguistically valid, that you are getting the best performance of the automatic summarization systems, even with the newer approaches and newer models, which we're going to cover in the course of the couple of lectures about text summarization. You still are talking about 15 to 30% ideally. Talking about other use cases for text summarization, news summarization is a thing. So they perform a gist or a summary of the news, or a summary of what is the news article is talking about, maybe a TLDR in the beginning. Academic research summarization, maybe you've also passed through different papers, different research papers within the field right now, that you are overwhelmed with the amount of information that is there. And if you get a gist, if you get a Medium article, if you get something that is summarized over the internet about it, you're also getting the idea behind it more or less in a summary. business meeting minutes, and like if you have a meeting which is running for like 1-2 hours, like in normal corporate world right now, this is actually, if you get an output like the meeting minutes in the end in a summarized manner or in a concise manner, this helps the people very much afterwards in understanding what happened within the meeting. Another thing is actually my research aspect is I'm working on an automated journalist problem, which means that if a journalist writes a query about, let's say, the elections, then he gets summary of what's happening maybe on social media with respect to the elections. What are the opposing point of views contrastively summarized? How does it go over a timeline, like from year X to year Y? How did the topic change? What were the major components and the summary of the major key points? What were the main things that are covered? So that also how is the summarization concept is integrated within my research field. So let's start by actually humans process for generating summary. So if you have a document, using actually your linguistic competence and extra linguistic knowledge, you start by an understanding phase. You understand what the problem is and understand the source text. And then you digest the information, you think about it, or you organize the things, and then you go into the phase of paraphrasing and writing. And after you selected the right information from the text or the thing you think it's important, you are actually paraphrasing and writing. Keep this in your mind. It's going to map into a lot of the NLP approaches to solve the problem. Is still mimicking the same person system. Talking about different summarization approaches, we have two major ones. First one is an extractive summarization, where in the extractive summarization, as you see out here, you try to select the most salient sentences from the input text and somehow use them to form the summary. So if you see here, denoted by yellow and blue, the blue ones are actually used to extracted and put into the new document as the summary of the problem. In contrast to the abstractive summarization, which is more generative, it generates new sentence to provide more coherent and hopefully fluent summary, often paraphrasing or rephrasing the original text. So if you see here, that's a very different color coding from orange to light blue. It's a very different outcome from the summary. Is a generated outcome, more or less, not an extracted outcome. Coming into an example out here, so that's the original text starting. I don't have to really read all of this, but if you see out here, the extractive summary gets the sentences which it thinks that it's important, which is like the red sentence, a team of researchers from the University of California, blah, 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 and then a phenomena in which two particles become linked, and so on and so forth. And it binds them together, it puts them into a paragraph, and that's the extractive summary. Whereas, if you go into the abstractive summarization, on the contrary, it actually paraphrases, and generates a new couple of sentences or paragraph which explains the thing. So researchers from the University of California have confirmed quantum entanglement and so on and so forth. You also see it can have actually words in common with the source text, but it's not extracted, it's paraphrased. Now, going into the different evaluation metrics and data. As per the sequence-to-sequence problems, you will have also multiple commonalities with the other sequence-to-sequence problems. Let's start by how a human would evaluate summarization. First, they actually defined multiple points for human-based evaluation of the summary, starting with the readability, that the summary must be logically readable and understandable. Then, by the structure and coherence, like it should have the coherent and related sentences together. It should make sense with respect to structure and coherence. It should be grammatically correct. If there are any violations of the language grammar rules, then it has to be penalized. It has to have correct referential clarity. So if Obama is identified by a he, then the correct pronouns should actually be referred correctly in that sense. Coverage, yes, we are talking about a lossy approach, but it should, as much as it can, cover the different topics in the input text. And with respect to the redundancy, it should not include any unnecessary repetition, because in that case, it's not concise anymore. It's not bringing the perspective anymore. And usually, one of the approaches doing that was through a qualitative evaluation from 1 to 5 for each and every point, from 1 being strongly agree to 5 being strongly disagree. And that is used to score the aforementioned quality metrics. But as you probably imagine, or as you probably know already, the actual human evaluation wouldn't be feasible at a larger scale. We need some approaches to actually evaluate how good a summary is. For that, BLEU, which stands for Bilingual Evaluation Understudy, actually started, or was one of the approaches that were initially developed to evaluate machine translation system, but was actually adopted to the summarization problem. Actually, the term understudy comes from the cinema world, more or less. So if you Google it, it's an understudy is a person who learns another actor's role in order to be able to act as a replacement at a short notice if needed. What does that mean? Like here, they started doing it in this understudy manner because this metric is actually learns is there to mimic the human evaluation and be there when necessary. And that's why it's called understudy. So, based on the computing, this metric is based on the computing precision, which is the fraction of tokens from the candidate sentence, the summarized sentence, that appear in the reference. With a high precision, meaning that most of the content in the generated in the candidate sentence is relevant to the output. How is actually covered is covered by precision is the number of n-grams in the reference summary appearing in the generated summary, which is denoted here by m, divided by WG, which is the number of n-grams in the generated summary. This is actually calculated afterwards with a geometric mean of the n-gram precisions, as denoted here. So is calculated from n equal 1 to n, which are like, if we're talking about 4 grams, for instance, then it's the unigram by gram, and so on and so forth, where we get the geometric mean of the outcome. Then we actually multiply by the BP. What is the actually BP is actually multiplied by a factor which is originally actually coming from the machine translation world, is the brevity penalty, which penalizes the translations that are too short, or the outputs that are too short compared to the reference. And this was hypothetically originally designed to compensate for the fact that the BLEU is only depending on the precision and has no recall term. How is this calculated? This is actually pointed to 1 if the length of the candidate is greater than reference, and then calculated as exponential 1 minus r, which is the number of words in the reference, divided by number of words in the candidate, if the candidate is less than or equal r. Next, going to an example. This example is actually kind of popular within the summarization domain. So this cat and the mat you probably see a couple of times over the course of summarization. So if we talk about the reference sentence being the cat is sitting on the mat, and the candidate sentence being the cat sat on the mat, means that this is the summary of the cat sat of the mat is the hypothetically a summary of the cat is sitting on the mat, and we want to calculate more or less the formula for that. Then we're going to go with 1 gram precision, which is the cat, like the m here is going to be equal to 5, the like example of how do we use BLEU. The reference sentence here would be the cat is sitting on the mat, which is provided by the the summary, which is actually provided by the human at that perspective, hypothetically, or the reference summary, or what we want to reach ideally. And the candidate sentence provided by the system would be the cat sat on the mat. If we go to the 1 gram precision, then we want to actually get the number of the n grams in the reference sentence that appear in the generated or in the candidate sentence that's going to be, in our example, the cat on the mat, which accounts to 5. So m here is going to be 5, and then wg, which are the number of n grams in the generated summary, is going to be 6. So we have 6 words in the generated summary, so we can calculate the precision as 5/6 being average 0.83. Getting this to the bigram or the 2 gram precision, then there's going to be m is going to be 3, like the cat on the mat, and the number of bigrams in the generated summary is actually still 6. Then the precision is actually going to be 0.6. If we're going to go to the 3 gram precision or the trigram precision, then we only have 1 trigram which actually coincides or appears in the reference summary and in the generated summary, which is actually on the mat. So that makes it 1/4, which makes it 0.25. If we go to the 4 gram precision, then this actually gonna be 0/4, which is actually gonna be 0. Here I'm actually using a simplified version of the mean to calculate the mean between the unigram, bigram, trigram, and the 4 gram precision here. Otherwise, you could also use the same form of the geometric mean, and apply a smoothing factor, because to accommodate for the 0 or for the case that we have right now with the 4 gram precision. This is going to appear in the tutorial. However, exam-wise, is going to be okay. It's going to be sufficient if you demonstrate the mean as presented out here. Yeah, so next one is the METEOR. And METEOR stands for Metric for Evaluation of Translation with Explicit Ordering. And here, they actually introduced 2 different perspectives with respect to the metric. First one is that they included an F score, a harmonic mean between the precision and the recall. And then they also included a penalty term to accommodate for this explicit ordering. So let's see. Precision, how are we going to calculate it? Again, number of unigrams in the reference summary that appear in the generated summary divided by the number of words in the generated summary. And this would, again, mean that most of the content in the generated summary is relevant. However, introducing the recall metric out here would be calculated as the same M over the number of words in the reference summary. And that would actually mean that most of the content in the reference summary made it into the generated summary in the end. Going into an F score, the METEOR is calculated by 10 times P times R over R plus 9P multiplied by 1 minus penalty. And here it comes the penalty terms. The penalty term is actually denoted by 0.5 times C over M. C here actually being the number of chunks, or the largest contiguous sequence of words in the candidate sentence that appears in the reference sentence. This actually would be clearer in an example. So if we get a reference sentence and annotated a provided sentence being on the mat sat the cat, in the candidate sentence by the system being the cat sat on the mat, then our matches are easy, right? The cat sat on the mat. Calculating the precision then is going to be number of unigrams in the reference sentence that appear in the generated summary is going to be 6. And then the number of words in the generated summary is going to be 6. And then the recall is going to be, again, M over the number of words in the reference summary, which is in this example also 6. And then an F1 score, or sorry, not an F1 score, but an F score would be here 1. However, the penalty term is going to be calculated by the number of chunks or the largest contiguous sequence of words. So here on the mat is appearing on the same order here. The cat is also appearing on the same order. And then sat is appearing hypothetically also in the same order. So in that case, our chunks are 3 over M again, which is going to be 3 over 6. Calculating the penalty then is going to actually be 0.5 times 3 over 6 to the power of 3. And then the METEOR is going to be calculated by 10 PR over R plus 9P times the penalty terms. Then going to the ROUGE score. It is actually ROUGE. ROUGE stands for Recall Oriented Understudy for GISTI Evaluation. It's still an understudy. Is the most popular evaluation metric for automatically generated summaries. So if you probably passed by a summarization-based paper or a paper that actually evaluates a summarization method, then most probably you will find ROUGE out there reported. The basic idea behind this is actually to count the number of overlapping tokens between the reference summary and the generated summaries. This actually is done via multiple approaches or different approaches like n-gram word sequences and so on and so forth, which we're going to actually go into in the next slides. Again, we're talking about recall, precision, and F1. So recall is overlap over reference, precision is overlap over candidate, and F1 is the F1 score calculation between the recall, the mean between recall and precision. Different ROUGE variants. Let's actually see how they are. First one is actually measuring an overlap of the n-grams, being unigrams, being bigrams, being up to the evaluator's choice. Second one is measuring the overlap of the lowest common subsequence between the reference and the generated summary. And the third one is going into the skip in n-gram. Let's see how this is with respect to an example. So here, if we have the reference sentence being the cat sat on the mat, then if we are measuring the overlapping unigrams, we are actually here measuring 5 over 6, which is the number of n-gram overlapping counts, the cat on the mat, over the total n-grams in the reference for the recall. We're going to do the same overlaps divided by the candidate for the precision, and then we're going to calculate the F1. Going to the bigrams, this is actually calculated by the overlap of the bigrams with respect to the reference and the candidate sentences, that being the cat on the mat. Those are the overlaps. And then if we calculate the bigrams in the reference sentence for the recall, for instance, is going to be the cat sat on the mat, and there is 5. So this is where the 3 over 5 comes from. Precision is calculated the same way, and then we're having the F1. Then we go to the LCS, the longest common subsequence. The longest common subsequence between the reference sentence and the candidate sentence is the cat on the mat. What is that? This is actually the longest subsequence meaning that like on the subsequence structure, like the longest common subsequence going with respect to the reference and the candidate. So if we go to our example here, the cat, then here sat and is are not the same, but it's still fine. Our subsequence is actually going again with on the mat. And so here is going to be calculated as the length of the longest common subsequence being 5 over 6 again, the reference length for the recall and the candidate length for the precision, and then calculating the F1. And then going to the skip bigrams, which is also an interesting measure in that sense. Here, let's get what are the skip bigrams in the reference. To start, let's get the bigrams, the normal bigrams. Is going to be the cat sat on the mat. But then we are calculating the skip bigrams. What is that, more or less? So I skip here cat, and is going to be here the sat. And then the next one is going to be cat. The next one is going to be cat on. The next one is going to be sat day, and then on mat. So let's go also to the candidate and see how it is looking like. So normally the bigrams are put as they are, and then we are then skipping cat, putting the is, then skipping on, skipping is, then it's gonna be cat on, and so on and so forth. And then the overlap skip bigrams from both the reference and the candidate are gonna be the cat on the mat, cat on mat. Like the skip bigrams appearing in the reference and the candidate is still one way to measure a common subsequence between both sentences with respect to the reference and the candidate. Yeah, now we saw like 4 different ways or approaches to calculate the ROUGE. Probably you are now thinking, okay, now all of those methods or all of those approaches are built on overlap methods, or the sentence, the reference sentence and the candidate sentence should ideally have the same words to have a high score. But then if we go a couple of slides back, we talked about abstractive summarization and extractive summarization. So you're thinking like, hey, maybe with the abstractive summarization is not always going to be the same. But yeah, I hope this is a thought that you're having currently about the metrics, which is actually a point in the metrics that is currently mentioned as as an issue or as a deficit or as a problem with respect to the evaluation metrics in the research. So is that more or less overlaps or like direct overlaps are the ones which are praised or given a higher score with respect to the methods. And still, as I mentioned, ROUGE is the actual standard for the summarization. If you remember, on the machine translation lecture, you went with the BERTScore, where you actually calculated token-wise cosine similarity of embedding representation. The embedding would then calculate the contextual meaning or the contextual nature with respect to the reference sentence and the candidate sentence. And then by that, you are not actually dependent on the overlaps, but you are more dependent on the meaning or the context if the embedding is able to catch that earlier on the state. And here what I did is that I passed the same cat sat on the mat and the cat is on the mat to a BERTScore embedding and calculated the cosine similarity. And this is the outcome that I got. Really overwhelmed with the different metrics that we are talking about. That's why let's go to a comparison point between the different ones right now. So talking about BLEU, this measured the n-gram overlap with an emphasis on precision. The guys in METEOR introduced a penalty for incorrect word order. So they had an ordering focus, plus they added also the recall. ROUGE, they measured the n-gram overlap with respect to different count methods. We talked about the n-grams, we talked about the LCS, we talked about the skip n-grams. And then the BERTScore used the BERT contextual embedding to compute the text similarity. Strength is, BLEU was simple and easy to compute, however, but the weakness that it's not originally designed for summarization. Also, you might have considered that with taking a look at the brevity penalty. That is, summarization requires substantial shortening of the text, which is not the case in the machine translation, which was the original thing that the BLEU was presented for. METEOR actually provides a more comprehensive evaluation, considers the order, also considers the recall, and then weaknesses that is actually still reliant on the surface level text similarity, the overlaps, but not deeper semantic similarities. ROUGE is the most commonly used. They designed different methods to capture the content overlap rather than only the overlapping n-gram count. However, it still does not capture the semantic similarity beyond the exact matches. The BERTScore can potentially capture the deeper, more semantic similarities than the n-gram overlap methods. However, this method is less established in the research with respect also to that, if you are doing a new algorithm in XYZ or inventing a new method, you have to score against the previous approaches. And this one is less established, so you find it less with respect to the evaluation metrics. Still, the focus is on ROUGE, and it might not always necessarily correlate with the human judgment of the summary quality, or might. So, but with some correlation studies that have been done on the BERTScore, it might not always be. Like, there were some cases that it was not correlating with the human judgment of the summary quality. Yeah, so getting from metrics, let's go to our datasets. First established dataset is the CNN Daily Mail. The summaries over there are abstractive and written by the article. They are mentioned as bullet points that the article publisher claims that it covers the salient information in the article. They are extracted from CNN and Daily Mail websites and is widely used in the abstractive text summarization models. With respect to statistics, it contains about 300,000 training examples, 13,000 validation, and 11,000 tests. And the documents in the datasets have an average 766 words, while the summaries are 53 words. I hope you are calculating more or less the T right now, or the tau we presented in the beginning. And this is an example of the CNN Daily Mail dataset. Next one is the XSum, the extreme summarization dataset. Why is it an extreme summarization dataset? Is that actually the summaries are shorter and more abstractive. They claim to be more abstractive than the CNN Daily Mail dataset. And actually more abstractive is measured by the novelty factor here is actually presented by the new words which are included in the summaries. And that's how they claim to be more abstractive. Each article has the summary professionally written by the author of the article, which is about 23 words on average, with the documents being 400 words on average. Dataset has about 200,000 training pairs, 11,000 validation pairs, and 11,000 test pairs. And yeah, that's how they claim in the XSum paper. By that, we actually covered the definition, summarization, problem statement. We built up the intuition. We talked about the evaluation metrics and the data within the domain. Let's actually go into a sample extractive summarization pipeline. So we have the text going in. We go through a content selection approach. So we want to choose the sentences that actually have salient or informative words. With a study that actually dated towards 1958, this is how they design more or less an extractive summarization pipeline linguistically to generate abstracts. How do we define the salient words? We actually calculate the TF-IDF, where we weigh each word in the document by the TF-IDF and add the words TF-IDF per sentence and choose the top n sentences. This is a way of representing the most important sentences or the top n sentences for the content selection approach. Next, we want to do the information ordering. We have 5 sentences right now, and we want to order them. First basic approach, let's present them in the same order they were presented. Just get them after each other. And then sentence realization, we need to do some sort of concatenation. We can just glue them together. And by that, we do have an extractive summary. Easy first approach. But then actually going into more complex approaches, they actually started with, or not started by, but a common approach to do that is actually the TextRank. TextRank is based on PageRank. I hope you actually remember PageRank by now. This was an algorithm that was first invented, I guess, by Larry Page back in the times to actually denote the web pages that are most important or very important with respect to the inbound and outbound links of that. If you think about this approach, this could be still applied to our sentences domain, right? We want to see which they wanted to see which web pages are important according to the relations with other pages, and we want to see which sentences are important according to the relations with other sentences. And that's how the intuition of TextRank came through. So with respect to sentence tokenization, the first step would be breaking the document into multiple sentences with the full stop. And this is how it looks like right now in our example, from sentence 3 to sentence 24. And then build the graph, where each sentence in the text is considered a node. And the edges between the nodes are created based on the similarity. So here, the similarity is the count of the words which are within sentence I, sentence J, over log the count of sentence I and sentence J. An iterative algorithm where each node sentence is assigned a score. Initially, it's 1 for all the nodes. Then the weighting of the graph is applied to the graph-based ranking formula. Here, the formula is denoted as the score of vertex I is equal to 1 minus d plus d, this is actually a damping factor which is set to 0.85 in the original PageRank paper. And then we are multiplying by sigma for all the vertices which are pointing in to vertex I. Vertex I is our sentence, and Vj are all the sentences which are having a similarity or a connection towards vertex I. Whereas we divide the weight of the connection from Vj to Vi, which is the similarity, over the sigma of Vk, whereas we sum over all the outbound vertices, or the similarity of sentence, as to all the outbound connections, more or less. Whereas again, Wjk is the weight of the connection from sentence J to sentence K. And then multiplied by Svj, which is the score of the vertex J, and do that again for all the vertices inbound towards vertex I. And then this is being an iterative algorithm. We do that for a fixed number of iterations or until convergence. Like when for the convergence it might be that when the scores do not change within like as per the iterative algorithms, did not change with a certain factor, this is actually stopping, or is done for a certain number of iterations. And at the end of those whole iterations, we actually have a graph of the sentences where each sentence has a score calculated by this big formula that we presented in the previous slide according to the similarities to the other sentences. And then we actually have to extract the top end sentences, and those top end sentences, which we extracted in the very basic approach by the TF-IDF, we just extract them and form the summary out here. And this is how, for our example, TextRank presented the summary. Talking about the pros and the cons of TextRank, TextRank with an unsupervised nature, it does not really need training data and is language independent. Like for the whole approach you saw, is based on overlaps, is based on similarity metrics, it can be used for any text in any language, in any form. And the similarity metrics is simple and easy to compute. But it does not consider really irregular words that are in one sentence and not in another. Long sentences are also unfairly rewarded, as the long sentence, if we have a sentence of 20 words and a sentence of 3 words, then you have more chances in the sentence of 20 words to match words against other shorter sentences, and those where at this point have a higher score. And now we are also talking again about the natural frequencies or the rarities that they are not considered by TextRank. Again, we're not talking about right now semantic metric is more or less done irrespective of the semantic understanding. And this is where LexRank comes into place. So LexRank, what it does, it changes TextRank in order to modify the similarity function to use something that would better get the language with respect to the TF-IDF. So that hits the rarity perspective, that also hits the linguistic factor or the linguistic nature of the words, and it more or less this calculates the cosine similarity, which is the dot product over the multiplied lengths, and is actually bringing out a different similarity metric to provide better results with when dealing with a single language corpus. Like if you're using, for instance, English, only English right now, since it now has more information about the semantic and more information about the contextual similarity. And by that, we actually conclude our chapter, or no, our chapter, yes, for the graph-based algorithms, where we talked about TextRank, and we talked about LexRank, which is more or less a variation of TextRank with a different similarity formula. Then let's go beyond conventional. Let's talk about BERTSum for extractive summarization. I hope you all know about BERT, right? So for BERT, we are calculating the contextualized embeddings. And with respect to when we are using the BERTSum, they actually denoted the document. Let's denote the document as D, having multiple sentences from sentence 1 to sentence M, and make it classification problem where you are assigning a label between 0 and 1 to each sentence I, whether this sentence will be included in the final summary or not. This means that we are more or less getting an output from BERT and then adding some summarization layer towards denoting an output from Y1 to YM with respect of like, hey, will this sentence be important or not? Getting from BERT to BERTSum, if you remember the CLS token, it's added before each sentence in BERTSum. Instead, in BERT, it was added once. What was the importance, or what was the reason for this CLS token? It was capturing more or less the context of the whole sentence. And when they do it here, they also capture here the context for the whole sentence. Also, they do capture a little bit of the relation, but we can use the CLS token as a representation for each sentence or for each T. The SEP token is added after each sentence as well. And then a segment embedding is also applied out here with that actually separates between different sentences, like you see here, EA, AB, and then reflects back to EA. And we still have our positional embeddings, which are going from E1 to EN. Then after the layer, after the summarization layer, we have multiple tokens, being the TCLS, that would ideally tell us whether this sentence is important or not. So, yeah. So here, after passing the sentences to BERT, or through the slightly modified version of BERT, we get T1 to TM, whereas those are the representations for the sentences that we provided to the BERT embedding. Then we say, like, through a specific, through some layers, through some fine-tuning out here, we get an outcome or a final predicted score of the different T's. And in that perspective, the loss of the model is a binary classification entropy. We said it's a classification problem throughout fine-tuning. And the the first approach they did is that they did a sentence scoring via a simple classifier. So they actually added here a simple classifier, and they fine-tuned with it towards finding or getting in the end the Y's representing whether the sentences were important or not. By this is going to be the linear layer added over the BERT output with the sigmoid function for sure. Did the downstream task, they fine-tuned by the downstream task towards classifying whether the sentences are important or not with respect to the and use this linear layer that is added and presented in the original BERT paper as one of the standard approaches towards utilizing BERT on a downstream task such as classification. But then they also went one level deeper, and they, instead of putting single linear layer or a linear layer, they actually presented an inter-sentence transformer. And this inter-sentence transformer is supposed to calculate the attention again right now, attention score between the different sentences that are denoted right now by the TI to TM. And so a normal multi-head attention operation is actually applied over here with a final output layer with the sigmoid function again. And they said they actually, from the paper, they actually found out that the L equal 2, or the 2, like having the L equal 2, where L actually is the number of layers of the transformer, performs the best with the inter-sentence transformer. In that sense, we start to calculate or to report the ROUGE 1, ROUGE 2, and ROUGE L for the CNN Daily Mail dataset with the classifier and with the transformer, which shows a better performance or a slightly better performance with respect to ROUGE 1, ROUGE 2, and ROUGE L. By that, we finalized the lecture from today. A minimal approach would be to work with the slides. A standard approach would be skimming reference 5 and 7. And an in-depth would be going through the slides and reading references 5 and 7, which are denoted out here being the LexRank, because more or less it covers TextRank plus the additions that they did for LexRank for the semantics similarity, or the semantic, or taking into account the semantic based characteristics. And 7 being fine-tuning BERT for extractive summarization. Thank you, and see you next time.